Okay, sorry about that. Whenever you hope stuff works, it doesn't. Okay, so I'm here to talk about kind of an overview of photovoltaics or solar cells. I understand that you guys have some background in semiconductors, and so I don't need to go too deep into that aspect, and I can assume that you guys know what semiconductors are, and is that fair? Sweet. Okay. So I'll talk about, again, what are photovoltaics, where they're used, why do we want to use them, what the current statuses of PV is in the world, and then how do they work, how do we measure or quantify the efficiency or quality of those solar cells, and then I'll kind of tie in, we'll talk about the science of PV, and then we'll talk about kind of engineering of PV. So what kind of solar cells are out there, and what kind of engineering went into making champion devices. So the idea, kind of so we'll talk about, there is the really basic engineering to make the solar cell, but then we have really advanced engineering to make good solar cells great. So we'll talk a little bit about that. So as an overview, most of you probably know, what's unique about a solar cell is it's a direct converter of light into electricity. So kind of like a backward LED, where you have some power source, a battery that is fed. You give a power source to a semiconductor diode, and that emits light. In this case, we have a semiconductor diode absorbing light and creating electrons or electricity. So that's the basic idea of what a solar cell is. And so the key idea here is it's a direct converter of light into electricity. So you can really think about every power source we have on the Earth is light powered by light. And I think that gives kind of a good kind of base comparison when you're looking at efficiencies of PV versus efficiencies of other power sources. So fossil fuels, as you may know, occur by photosynthesis. So plant organic matter absorbs light. It turns that light into, it grows, and over millions of years after they die and decompose and under heat and pressure, you get fossil fuels. So if you look at kind of the overall efficiency of fossil fuels, and that's kind of the easy one to poke at, you can look at some are a few percent. So I think that it depends on what you assume the efficiency of photosynthesis is, but essentially you're looking at a few percent efficiency. So obviously the efficiencies that they quote for fossil fuel plants that are somewhere around 50%, that does not take into account the kind of overall absolute efficiency of that power source. So PV, like I said, directly converts sunlight through a solar panel, which are getting more and more efficient. I'll talk about that. And then through a relatively efficient inverter, if you're putting it into the grid. If you're using kind of direct PV on your house to power a battery, and you can just use DC power, then you don't need to worry about this aspect. But you get because you're converting light directly into electricity, you can expect much higher efficiencies. If anything I say confuses you, please stop me and tell me to repeat. So where are they used? Kind of the old school calculators, you have solar farms, in space applications, rooftops, utility projects throughout the city, kind of remote locations that don't have a grid. So solar is becoming more and more ubiquitous. These are some NASA flight, and they're starting to try and make solar cars. And those are concentrator panels. So those essentially use concentrated light to heat up either water to make steam, turn a turbine, or they'll heat up some sort of molten salt is a really common one that you essentially store the heat in a more efficient medium. Let's see. So this is a former professor at the U. He drives these little solar trucks. Ecotrikes, which is kind of a cool local application of solar. So what is the largest solar utility scale right now? It's in China. China is the single largest manufacturer of solar panels, primarily silicon. And so they have two big solar farms. One is 1,500 megawatts. So to put that in perspective, that's about 200,000 households. That is completed. They have a second one of 1,000 megawatts, and they're expected to grow to 3,000 megawatts. So these are huge solar farms that are being installed all over the world. So that was the two biggest, and they are 2 gigawatts about of production power. So right now, to put that in perspective, we have about just a little over, that was 2 years ago, so this is continuing to grow. We're probably pushing 300 now gigawatts of production capacity. And solar grows exponentially, has been growing exponentially for decades, and it's not expected to slow down as prices continue to drop. And solar becomes kind of a more economical decision for power generation. So if we talk about what the potential of PV is, and this is kind of the motivation of why you might want to use solar, and what the motivation is that you know, you might have heard kind of the catch line of solar is that in an hour, half an hour, the sun provides enough energy to power the world. Obviously, that's an oversimplification in terms of how you harness it, and you know, most of that is not on land and it's in remote areas. But if we say that the flux of solar is estimated at about 90,000 terawatts, and our global primary energy consumption, these are rates, is 20 terawatts in a year. So if we assume 17% conversion efficiency, which is now what pretty standard modules are achieving, then we need a fraction of a percent of the sunlight would be needed to meet global power demands annually. And so if we look at a map of the United States, I want you to just think for a second of how big, let's say we could make one big single solar panel at 17%, and it would meet the world energy demands. How big do you think it would have to be? Any guesses? Kansas, you can participate. Okay. Anybody else want to guess? No. Okay. Fine. You guys are no fun. Okay, so it's about the size of Texas, and obviously Texas is an enormous state. But if you look at the world as a whole, it puts into perspective that you know, solar is capable. This doesn't take into account kind of mining bottlenecks, and some solar cells use minerals that are rare. So, but to put into perspective, kind of how big of a panel you need to this would cover all primary energy consumption. Some primary energy consumption is obviously fuel from cars. So an oversimplification, but just so you have an idea of kind of what the potential of solar is. And so, like I said, over the past few decades, we've had a significant drop in costs of photovoltaics. So on the x-axis, you have the cumulative production, which I've shown has been growing exponentially. It's on a log scale. And then you have the module prices. So the blue, and I'll talk about this in a second, the blue is silicon. Silicon is kind of the workhorse of, it's the standard. It owns over about 90% of market share. Thin film technologies are, I'll explain what the difference between those, but they're kind of a newer generation, and they compete in cost now with silicon, and they are cheaper to manufacture. You can see that these costs have continued to decrease over time, and solar is just becoming cheaper and cheaper. And actually, so this red line here is the U.S. government Department of Energy puts out what they call sunshot goals every 10 years. And so if we approximate this cost, this red line is where they want to be in for, I believe it's utility scale for 2030. And they had goals for 2020. And their utility scale, where this was just a few weeks ago, they reported that their goals for 2020 have already been reached. So research is still going strong, and you can see what the costs of these were not even a decade ago. So there's a lot of engineering going into PV making them cheaper, such that it can reach grid parity, and solar ceases to become a moral decision for people and more of an economical decision. Okay, so let's talk about what materials make solar cells. So in the top left corner, we have kind of the spectrum of light that hits the Earth. So the yellow is if you're at the top of the atmosphere, kind of what spectrum you'd see. You may know it can be approximated by a black body radiation, which is the gray curve. However, the atmosphere absorbs significant radiation. So what we use down on the ground is known as air mass 1.5 spectrum. So essentially what the red curves show is primarily what water vapor absorbs of incoming radiation. And so actually what you approximate for the solar spectrum is not what you see at the top of the atmosphere, obviously. Anyway, so we have kind of three classes of materials. We can have, based on, are you guys familiar with a little bit of semiconductor physics? Yeah, okay. So in metals, we have overlapping valence and conduction bands. Semiconductors, you have a small forbidden gap between the valence band and the conduction band, and insulators, a much larger, essentially, energy gap. So solar cells have to absorb light to create electricity. So if we look at the incident PAM 1.5 spectrum and calculate the available maximum current and voltage, so solar cells are diodes, and so when you're operating them, you have to produce both a current and a voltage, right? So current comes from simply how much light can you absorb. So the blue curve, I should put arrows here, but the blue curve is to the left side, and that's the current, and the voltage is shown here on the right. So you would expect the smaller band gap, if you're looking at incident spectrum, the smaller the band gap, the more light you'll absorb, right? Because you're going to absorb any light that is above the band gap of the solar cell, or the semiconductor that you're using as your light absorbing layer. Does that make sense? So in theory, the smaller the band gap you have, you can maximize your current. But at the same time, the smaller the band gap you have, the lower the potential voltage that you can get from your semiconductor. And so you might expect that you want to balance these two. So the larger the band gap is, you're pushing into almost the insulator range, you can get really high voltages, but you're going to get no current just because you're only absorbing really high energy photons. So you might expect, if you kind of multiply those curves together, that is the power, and then you can divide that power by the incident spectrum, and you can see this is what's known as the Shockley-Quasar limit. It's essentially the maximum power that you can get from a photovoltaic, a semiconductor, based on the band gap. So, if you look at, it's not surprising that you kind of want to hit this sweet spot region here where you're maximizing your current and your voltage, right? About 1.5, and you see that at about that range, you're getting somewhere a maximum efficiency of about 30 to 35%. And so this is this is like one of the first steps of trying to pick a new material. What's the band gap? What's the maximum efficiency that I'm going to be able to get from this material? Okay, so a solar cell needs to do three things. I just talked about the first one. It needs to generate charge carriers. So that's absorbing sunlight. Yep.
Is that IV curve just for silicon, or is that a general IV plot for all?
This one?
That one, yes.
So this is not an IV plot. This is this is for anything.
You're right. But
Any semiconductor, any material that has a band gap. So silicon is about, and actually I didn't mention these lines, but these lines show different common semiconductor materials. So silicon has a band gap of 1.1. So you can see where it lies. Gallium arsenide and cadmium telluride are thin film.
yeah, that's why I didn't see that.
Yeah. So this is actually standard thin film solar cell stack, but they're quite similar to what silicon uses, but it's just for an example. So like I said, we need to generate charge carriers from, so you have light coming in, and you make an electron hole pair. So an electron is excited from the valence band into the conduction band. You have an electron hole pair. But if that's all it does, then your solar cell is useless, right? I mean, just generating a pair. If a semiconductor is put in light by itself, that whole pair is created, and then it'll recombine. So you need to separate them. And so how do we do that? And I'll talk about that, but we use different materials to set up an electric field to separate the charge carriers. And then we have contacts to collect those charge carriers to do electrical work. And so the resistance of your load will depend on where you're operating on your, if you are thinking about a JV curve, which we'll talk about in a second, but the resistance of the load will come in and determine the operating point. Okay, so briefly about kind of pn-junctions, which are kind of the backbone of inorganic photovoltaics. This is true for silicon or gallium arsenide or CdTe. Any kind of solar cell uses these pn-junctions because, I'll talk about it, but because for charge separation. So when we use two different types of an N-type and a P-type, have you guys talked about pn-junctions? Okay, so pn-junctions, we can have an electric field that will separate electrons and holes such that they can be put across the load. So when we take intrinsic semiconductors, the Fermi level is kind of a measure. It is the point in a semiconductor or the Venn diagram at which the occupation probability is 50%. So for an intrinsic semiconductor, Fermi levels are in the middle of Bandgap. Have you guys talked about Fermi levels? Okay. You got it. Does everyone know? Has everyone heard about that term? Okay. So yes. So an intrinsic semiconductor, when the valence band is completely full, so you have no excitation, and the conduction band is completely empty, your Fermi level is at mid-band gap. So that's technically where your occupation probability is 50%, assuming a Fermi statistics. Does that make sense to everyone? Okay. So as we add atoms, impurities, or dopants into, so if we look at, this is for silicon, if we add a phosphorus atom, that is a group 5 element, so it has an extra valence electron, we essentially add an excess of electrons, and we can dope silicon N-type, which just means that you have extra free electrons. Same thing is true if we add boron, which is a group 3 element. It has one less valence electron than silicon. We essentially add a hole. So a hole is kind of a theoretical concept in semiconductor physics that simply implies the absence of an electron, so a positive charge carrier. So as we dope these, let's say silicon, both P and N, what will happen is we will put holes into the valence band or electrons into the conduction band, and that will push the Fermi level towards either the conduction or valence band. When those are brought together, first, when a p-junction is brought together, you have just a huge concentration gradient here. The N side has a huge concentration of electrons. The P-type has a huge concentration of holes, so you get simply some diffusion problem. Electrons want to flow from N-type into P-type, and holes want to flow from P-type into N-type. Does that make sense? What those leave behind is fixed point charges. So where you've added extra free carrier holes and electrons before diffusion, after diffusion, you leave those atoms behind that are in a charged state. So does that make sense? So where you have phosphorus with an extra electron, that electron diffuses away, and all of a sudden you have phosphorus with a positive charge on it, and that is fixed. So you have a built-in electric field there. You have a potential difference, and so what happens in the Venn diagram when you bring these two semiconductors together? The Fermi level must be constant over the over the width of the region, and you have band bending, and so you have a region where any electrons and holes are going to have a force of an electric field put on it. And so any electrons or holes that are generated within this region of band bending in the band diagram can be separated and then collected. Okay, so that's why the pn-junction is the backbone of any inorganic photovoltaic and crucial for PV operation. So when I'm looking at band diagrams and trying to understand them, a good thing to remember is electrons like to roll downhill. I kind of think of them as boulders. So in a band diagram, electrons will roll downhill towards the N-type semiconductor, and holes, you can think of them as bubbles. They'll float up, so they'll go towards the P-type layer. That's a good way to remember how electrons and holes will operate within an electric field in a band diagram in PV. So this is just showing again that operation. So we have absorbed light. We create electron hole pair that is excited into conduction valence band, and those are acted on by the electric field that's built in because of our p-n junction. Okay, so how do we characterize PV? The first, as I mentioned, these are diodes. So the most basic characterization is looking at the current voltage characteristics of a solar cell. So in the left-hand corner, we have kind of an ideal diode curve of a solar cell. The dark would be a solar cell in the dark. If you shine light on it, you get a shift in current. You start generating current, and so your IV curve just shifts down. So what this is showing here, if you remember the plots that I showed of the maximum current, the maximum current in a solar cell will always be at 0 voltage. It's a short circuit current. The maximum extractable voltage will always be at an open circuit voltage when there's no current flowing. So your maximum power point is a function of what your JV curve looks like. And so you're essentially trying to find your ideal power point, and this is where the resistance of your load comes in. So if the resistance of your load is too low, you won't be able to extract voltage. If it's too high, then you'll kill the current. So that's a really important optimization of the operation of your solar cell. So not only do you need to look at your JV curve and determine what the resistance of your load needs to be to extract the maximum amount of power. Does that make sense? Sweet. Okay, so if we look at an electrical diagram of a solar cell, we have our photocurrent source, we have the diode, and then we have the external load, and that's kind of the ideal picture of a solar cell. But we have some non-idealities, obviously, in real life. So shunting, we have series resistance, which can be contact resistance. It can be just bulk resistance of your material. That's straightforward. Shunting is generally due to pinholes, so you have essentially you're bypassing the diode, and so you have current that is flowing not through the ideal path, not through the external load. You have it shunting through less pathways of less resistance. So you want to maximize your shunt resistance so that you're actually flowing all the current through the load, and minimize series resistance so you don't have losses in other parts of your device. So if we look at the effect on JV curves of shunt and series resistance, shunt resistance primarily affects voltage. And you can see as you lower shunt resistance, you essentially turn your diode into a photoresistor, essentially. Series resistance is more strongly affects current. So as you increase that, you'll again turn it into a photoresistor. And fill factor is another quantity that's used to characterize solar cells. It essentially characterizes how square the JV curve is. So in an ideal perfect solar cell, your JV curve would be square. You wouldn't have kind of the diode shape. And the fill factor is what, essentially what percentage of that square you're attaining in your IV curve. So both of Shunt and series primarily affect fill factor, but they do it by affecting either current or voltage. Another really common way to characterize a solar cell is called quantum efficiency. So quantum efficiency is a measure of if an electron hole pair is created, how many of those, what percentage of those electron hole pairs actually flow through the load. So if you have a 100% quantum efficiency, that means every single electron hole pair that's created in your device is going through the load, and that's ideal. Okay. So this is looking at essentially QE as a function of the current and area in the field and the photon flux. But the cool thing about QE is that you can spectrally resolve it. So you measure QE as a function of wavelength. So whereas incident light on a solar cell is broadband, you pass that incident spectrum through a monochromator, and you can look at what wavelengths of light you're losing power. Okay. So if we look at this, we see that, and this is a silicon cell. We see right around the band gap of silicon, we're getting basically 100% quantum efficiency. So every electron hole pair that's created around the band gap is actually passing through the load. So you get some losses at higher energies here, and some losses at the back. So what does that do to? So primarily, you can simplify and say that, so at shorter wavelengths, higher energy photons, those are absorbed relatively quickly. They're absorbed towards the surface. A lot of that is due to recombination at the front surface. In inorganics, in thin film solar cells, where we have, and I'll show you the band diagram, where you have larger band gap semiconductors stacked on top of your light absorbing layer, you can lose QE from absorption of those higher band gap layers. So for example, cadmium sulfide is a common N-type junction partner for a lot of thin film solar cells, and that will absorb at a certain wavelength, and so you'll see a step in your EQE when that starts to absorb. Then you have in your infrared region, you can have either light that simply is too low in energy and it passes right through the solar cell, so infrared light, and it goes to or you can have recombination in the bulk of the cell. So whereas high energy photons are absorbed at the front, infrared low energy photons are absorbed deeper into the cell, and so you can see in your EQE where you have issues, which is a cool way to characterize solar cells. And so we can put this in a little bit differently here about, so if we remember the maximum efficiency curve that I had showed previously, you may have wondered why it's only 30%. Yeah, it seems relatively low for all the energy that you're absorbing, so where is the rest of that energy going? And so if we start at, this is the bandgap energy of the material, so essentially the maximum power efficiency possible is a function of that bandgap. You can lose energy in three primary ways. The first is what's known as the thermalization of carriers. So if you have a really low bandgap material, let's say 1 eV or less, there is an immense amount of light that you will absorb, right? Most of the spectrum is above that energy. But if you look at, so number 2 on this diagram here, you have a really high energy photon. Your electron is kicked way above the bottom of the conduction band. And if you know from quantum mechanics, electrons don't want to sit in a really high energy state. So particles will try and relax down to the lowest possible energy state, which for a photovoltaic is going to be kind of the bottom of the conduction band. And so when you're absorbing carriers, that are much higher than when you're absorbing light that has an energy much higher than the band gap, the carriers are going to relax down to the bottom of the conduction band just naturally. And so where does the rest of that go? That energy goes to heating up the solar cell. So you have phonons that are generated as they relax down and bond vibrations that will heat up the solar cell. So that, as you can see, this blue is more of a problem at lower band gaps, which makes sense because of a larger portion of your spectrum has energy much larger than the band gap. The second portion here is this red portion is kind of the opposite. As you push higher in band gap for your semiconductor material, there's a much larger portion of the spectrum that doesn't have enough energy. So you have sub-band gap radiation that is simply going to vibrating bonds, so heating up the solar cell, or it just passes right through it, so it's not useful energy. The third part is radiative losses. So those are quite small and more of an issue for smaller band gap. Because you're absorbing so much more light, your solar cell heats up a lot quicker, and then you have your solar cell acting as essentially a black body radiation. And so you'll lose some efficiency just simply based on radiative effects from your solar cell into the surrounding atmosphere. Okay, so this diagram on the right kind of diagrams some of these issues. So number one is light passing right through, so sub-band gap. 2 is thermalization of carriers. 3 would be kind of a loss in voltage as you pass through the electric field in the junction. 4 is your contact resistance. So depending on how your work function and Fermi level line up at your contacts, you may lose available voltage there. And so these are all efficiencies from efficiency losses due to simple device physics as you're building your cell architecture. So this, I should say that this maximum efficiency has 3 main assumptions. So this Shockley-Pfizer formulation. The 3 assumptions are step function absorptivity. So that means that there is a hard step function at the band gap, and every photon that at or above band gap is absorbed. Every photon at or below, just below the band gap, is not absorbed. Recombination is only radiative recombination. So I guess I could. So recombination is number 5 here. As carriers recombine, so an electron is created and recombined with a hole before it passes through the load. That's known as recombination. Radiative, there are two primary types of recombination. Radiative recombination means that when an electron hole pair recombines, it emits a photon. And if it emits a photon, that means the photon can be reabsorbed and you can start the process over. So it's not really a loss yet. If you have defect states that present energy levels within the band gap, so essentially allowable energy levels within this forbidden gap, you can have recombination via intermediate states that don't emit photons. So essentially, they emit phonons. So they just go up to heating. They just go to heating the solar cell. So this idealized version says that if we're going to have recombination, it's going to emit a photon, and that can be reabsorbed by the bulb. The third is a perfect back reflector. So if we talked about sub-band gap photons or any photons that aren't absorbed in the bulk of the material and they essentially hit the back surface, they could pass through the back surface, or basically the reflectivity of the back surface will increase the path length that light has through the material, so increasing the collection probability of those photons. Does that make sense? Cool. Okay, so if we look at this is an efficiency table put out by the National Renewable Energy Laboratory, looking at the efficiency of all different types of photovoltaics. So I like this comparison to automobiles, and it kind of is a simplified version. So we've talked about silicon. Silicon is kind of the luxury standard. It has a really high efficiency. Thin films are a cheaper alternative, and they're getting to be about as reliable as silicon. Organic PV, which I'll talk about, is really cheap, and not very stable. It could break down at any time. Multijunction cells I'll talk about as well. They're more advanced engineering and essentially stacking many PN junctions on top of each other, and those can essentially that's how you can surpass this theoretical limit is for a single junction. So as you get into more advanced engineering techniques, and you can stack multiple PN junctions on top of each other where you're absorbing light at specific different wavelengths, you can surpass this theoretical limit. And so yeah, I think of organic as kind of only when it's not commercially viable yet, just because its performance is not at the point where it makes sense to produce them commercially. So if we look, if we zoom in here, we can see, so in this region here, this is silicon and the top performing thin film solar cells, and those are performing comparably with each other now. And so solar cells have been divided into kind of three generations is what they call them. So this is the cost per square meter of photovoltaic material. The first generation is silicon, so that higher costs, and the second generation takes that cost down with comparable efficiencies. So that's thin films, and I'll talk about the difference between those two in a second here. This is the shocking Pfizer limit, and like I said, third generation uses advanced engineering techniques in order to surpass that theoretical single junction efficiency. So if we look at, this is from 2010, the market share, crystalline silicon and silicon together owns over 90% of the market share. Because silicon is one of the most earth-abundant materials. It's had 50 years of research. It's just really well known, and it works well. And it's hard to take market share from a technology that has proven to work very well. So if we look at these other two slivers here, cadmium telluride and CIGS, those are the two top thin film technologies, along with gallium arsenide, and those are gaining market share, but they're still second generation materials that there's still a lot of research going on to improve to lower the costs of them. Okay, so now we'll talk about the different classes of solar cells. I'll briefly discuss the different technologies they're in and some engineering feats that have been undertaken to improve the efficiencies of these cells that kind of aren't obvious routes. So this is a classic silicon type architecture where you have P-type silicon. Silicon uses a homojunction. You have silicon are about 200 to 400 microns thick, which is still really thin. But when I talk about thin film solar cells, you'll see why they're called thin films. So you have your front and back contacts on the front and back, and when it's manufactured like this, so the texture plus ARC, so ARC is anti-reflective coating, so that essentially you try to minimize your reflected light right off the top of the cell. Texturing is also a method of light trapping. So essentially you increase the path length of light through your device, and you can increase the collection probability. So as kind of the standard solar cell architecture here, you'll get about 15% efficiency. And if we look at the loss mechanisms here, so we had talked about recombination losses either at the front or towards the back. You get reflection losses because you're using metal contacts, so you're not absorbing over those areas of the light. And so one of the big, I guess I talked about a little bit about light trapping. So light trapping is one of these engineering feats that has been employed in in photovoltaics to increase the path length of light through a device. So you get reflections that essentially ricochet through the device. So you get many more passes. The light gets passed through the device many more times, and so you increase the collection probability. And here, this shows just an increase in current by increasing the path. So using textured surfaces to increase light, you can increase current significantly, simply because you're absorbing many more photons. So one of the coolest engineering feats that has pushed silicon into the 20s, 20%, a company called SunPower has kind of this interdigitated contact system. So both the front and back contacts are on the back of the solar cell, which means that you have a completely, and these are really easy to recognize if you see these out in the kind of outside, because you don't see any. Traditionally, when you look at a solar panel, there's a lot of grid lines on it, and these are completely black and completely. You don't see any contacts, and that's because in some really savvy engineering, they were able to essentially make these junctions at the back to so that they can put all their contacts on the back of the device away, and so they can maximize the absorption of light. These passivating layers are simply layers at interfaces are really common places for recombination. So voltage losses in the cell, and they use a silicon dioxide layer to passivate these layers. So essentially, clean up dangling bonds, clean up mismatches, essentially efficient transfers of energy between the interfaces. And so they were able to achieve, I think it's 23% for this type of cell architecture, and that's the world record right now for this type of monocrystalline silicon. Actually, it might be 25% and 22% for a module. But this is kind of the gold standard for silicon cells. And again, also this backside mirror, so this you minimize the light absorption at the back, you reflect it back into the bulk, and you absorb more carriers. Okay, so if we talk about thin film technologies, the three big players that I mentioned are gallium arsenide, cadmium telluride, and copper indium gallium diselenide. So the push for thin film really comes from a power density argument. So as I mentioned, silicon traditionally uses 2 to 400 microns, so still very thin. The reason they have to use, so silicon is an indirect bandgap semiconductor, which simply means that the conduction band minimum and valence band maximum are not aligned in momentum space, so in quantum mechanics. And so in order to absorb a light, so if we look at the band diagram of silicon, you can see how it denotes the band gap. The valence band maximum and conduction band minimum are offset in K space. So in order to absorb a photon of light, you not only need a photon with energy higher than the band gap, you need a momentum shift. So that generally comes from some phonon transition that imparts extra a shift in momentum into the excited electron. And because of that, silicon has really low absorption coefficients. So essentially, you need a lot more material to absorb the same amount of light. Whereas if you look at thin film technologies, they have direct band gaps, so it's a very simple absorption process. They have orders of magnitude higher absorption coefficient, and so you can achieve comparable efficiencies with 100 to 200 times less material. So you can think of it, if you take a semiconductor, a cubic centimeter of semiconductor, silicon, that would create about 50 square centimeters, and for a thin film, you get about a square meter. So you can think about, if your goal, we talked about how solar is incredibly, there's an incredible abundance of solar cell, but it's really dilute as it hits the surface. Our goal is to collect as much light as possible, and so the power density of thin film solar cells far surpasses that of silicon, which is why, from a materials usage standpoint and a power density standpoint, that's the motivation for second generation photovoltaics. So CdTe is the biggest competitor to silicon. And just recently we've had, so if you remember, the biggest silicon installations in the world, and these are the largest solar, were about 1,000 megawatts and 1,500 megawatts. So for CdTe, the largest installations right now, these are from a company called First Solar. And there is Topaz, I think, is in Santa Barbara. Agua Caliente, I think, is in Arizona. So made from collectively 14 million solar panels. So these are being commercially produced primarily by First Solar, but they are actually cheaper to produce than silicon. So right now, a lot of people are moving towards CdTe simply because from a cost standpoint. One of the biggest issues in solar manufacturing actually is initial startup costs. So when you already have huge manufacturing plants of silicon, it's hard to come in as a new player, and when you need hundreds of millions of dollars to start up. So CdTe, I think they have, I don't recall what their generating capacity is right now, but it's quite high, and they're continually expanding. So gallium arsenide is, from a device physics standpoint, is the best single junction solar cell in existence. So gallium arsenide is traditionally grown epitaxially. So you grow it on a wafer, a perfect gallium arsenide wafer, and you grow your single crystal gallium arsenide on top of that. And so you have essentially as close to a perfect semiconductor crystal as you can get. And if you look at it versus Bandgap, it achieves a power conversion efficiency over 86% of its theoretical maximum, which is pretty astounding. That being said, epitaxial growth is really expensive, and so it's primarily being used for space applications for two reasons. One, where cost per weight when you're sending stuff up into space is really important. You want to maximize your efficiency. So these are 28% efficient, the best that are made. And so where cost per weight is extremely important, you want to make sure you're getting the highest efficiency cell out there in space. The second is that these tend to be more resistant to the types of radiation you see in space, so high energy gamma radiation and other types of radiation that can damage silicon. For other technologies, gallium arsenide is a bit more resistant towards that. That being said, these are not made for kind of residential applications because the cost is so much higher. Okay, so I'll talk briefly about organic photovoltaics. These kind of have a different physics, device physics than inorganics, but they're popular because they're really easily manufactured from non-toxic materials. They're cheap to make. So in organics, the analogy to the valence band and the conduction band is the highest occupied molecular orbital or lowest unoccupied molecular orbital. So you still have light absorption in these photovoltaics, and they can be tuned based on their chemical. So you can really refine and tune the band gap of these materials through chemical design. So adding essentially adjusting the side chains and other organic structures will affect what kind of light it absorbs. So whereas inorganics have these continuous bands of allowable states, the organics have kind of still have discrete states, and we have the lowest unoccupied and the LUMO and the HOMO bands. And so that's essentially the one difference between organics and inorganics. The second is you don't really have band bending that's analogous. You have a little bit of it based on your band diagram up top, but the way that organics work is primarily by having hole selective layers and electron selective layers stacked on top of each other, so that when you create an exciton, which is a bounded electron hole pair, you need some sort of am I trying to say? You need some sort of driving force to separate that electron and hole pair. So in inorganics, where you have this significant band bending to drive and separate electron hole pairs, in inorganics, your band alignment is such that you have electron layer, hole selective layers and electron selective layers to separate those pairs, and then your external contacts. So organics are generally, they're used what generally is known as a bulk heterojunction. So in inorganics, where you have a very clean stack, one on top of the other, organics kind of have these. You can imagine, let's say the red is kind of your p-type layer analogy, and the blue is the n-type layer, where you're getting these charge separation within a bulk formation here. Any questions about organics? I already talked about them. So the newest class of inorganics are these what are known as perovskites. So they're essentially metal salts, and these, in the last 10 years, these have really exploded. There's a ton of research being done on them. They're kind of a hybrid organic-inorganic. So they have organic band structure, but kind of inorganic charge carrier properties. And there's been a lot of interest in them. What's kind of unique about them is they can be made really thin. And so if you compare the power per weight ratio, ultra-thin perovskites outperform any other existing technology right now. They have some stability issues, but this was kind of a research paper that put them on a self-powered plane. So they could be interesting for military applications where weight is extremely important. The reason that wouldn't be used in space is just because the stability, they're metal salts, so any water ingress inside the cell will destroy the cell essentially really quickly. And so they do not have the long-term stability yet necessary for space applications. So these are right now really, I think the stability of them is on the weeks scale, whereas standard silicon or other thin films standard warranty is about 25 years. Okay, so the last class that I was going to talk about is these third generation technologies, so advanced engineering that pushes you past the Shockley-Queisser limit, the maximum single junction efficiency limit. So the idea with multi-junction cells is that you have different pn-junctions, as I talked about, that are tuned to absorb at a specific wavelength. So this is kind of a maximum efficiency, essentially the same, a similar calculation that's done with Shockley-Queisser, but increasing the number of junctions. So the maximum efficiency they see, if you have 36 junctions, which would be incredibly complex to engineer, but you can get up to 70% efficiency. And so if we look at a QE curve, a calculated QE curve for a multi-junction cell, you can see that you can use, you have different semiconductors that are ideally tuned for different wavelengths of light. And so essentially, this filters out all high energy light, this filters out middle light, and the germanium collects all the low bandgap light. And so thereby you can more efficiently utilize the incident solar spectrum. So kind of an example film stack for this uses, so we had showed it, a low bandgap, middle bandgap, and high bandgap material. And these are made, I think, almost 40% efficient. And so these are expensive right now because there's a lot of advanced engineering that goes on. And as I had mentioned, interfaces are really common places for recombination and efficiency losses. So you have to be really precise with how you make these and stack all these different materials on top of one another. So a lot of multi-junctions are used in concentrator applications where you just get as much light on it as possible to push efficiency as high as possible. So some other advanced engineering techniques that I wanted to talk about One is it possible to push quantum efficiency past 1? What would that mean?
Have like a feedback loop, some sort of electron avalanche.
Yeah, sure. So there's a few ways that it's known as multiple exciton generation. So the idea is that one photon can generate 2 electrons, so that you could push the quantum efficiency higher than 1. So a few ways that this can happen is you can have one higher energy electron absorbed that relaxes radiatively between 2 intermediate states and emits 2 lower energy photons that are then absorbed by a third material. So then essentially you have one incoming photon generating 2 photons that can, so you can see how that's known as a down converter. So you take high energy light, and based on your material properties, you potentially could emit 2 lower energy photons from that one high energy photon. This is not exactly MEG, but the opposite of that would be two lower energy photons. So light that may not be absorbed naturally in the device if you have sub-bandgap light. So if you remember the ideal picture of efficiency losses, you can lose efficiency from sub-bandgap light. But if you have these, they're known as intermediate bandgap solar cells, that you can then absorb 2 smaller energy photons that can then emit essentially an up converter. So you have 2 lower energy photons that will emit a higher energy photon that can be absorbed by the material. So the last thing I'll talk about, and these are, again, efficiency designs. They're known as radial junctions. So you have these kind of nanotube wire arrays that you have the pn-junction in a radial architecture. So you can think of like a p-type core and an n-type shell. And so your diffusion lengths necessary in the devices are much smaller, so you can collect carriers more efficiently. All of these examples are just to point out some of the savvy engineering techniques that are being employed right now to push efficiencies away from past where they are right now. It's really easy to make a 5% cell 10%. It is really hard to make a 15% cell 20% because everything is already pretty good. And so sometimes you need to completely redesign what you're doing. That's, I think, is a pretty cool design. Okay, so yeah, PV has grown exponentially for over 2 decades. Some people like to characterize it by Swanson's law. If you've heard of Moore's law for transistors, Swanson's law says something like the price of PV is halved every time you increase generation capacity by 20%. And that's actually been followed quite well over the last few decades. So solar cells require 3 primary events. That's absorption of light to generate an electron hole pair, a separation of that electron hole pair, and then collection of the electron. So there are a lot of viable technologies that I've talked about a lot of stuff. So one material isn't going to be the answer to energy issues, and high efficiency takes really savvy engineering. So we've kind of entered the 3rd generation of PV where advanced engineering processes are going to start pushing efficiencies higher and higher. So thank you. If you have any questions, please let me know. Or if you want to know, my research is on thin film solar cells. So feel free to ask me anything about that or what I just talked about.